Hi there, this is Phillips of the Rochester Institute of Technology, Department of Motion Picture Science. I'll be talking today about the perception of animated exaggeration, some empirical experiments that we have done here at University of Giessen with Phillipp Schmidt and also at Skidmore College, where we look at simulation and we look at motion capture and how our perception of motion and reality are mediated by these. Hi, this is Phillips. Today I'm going to be talking about the perception of animated exaggeration. So here's a short film, extremely short film, entitled Bouncing Bowling Ball, which is pretty simple, straightforward. You know that it's a bowling ball based on its motion. There's some visual cues here as well in the depiction of the material of both the ball and the thing that it hits. And here's a animated adaptation of that film, which has the same dynamics, and physical depiction of the ball's diameter with respect to gravity, but there are definitely some hitches there. But there's no other information that was in the original thing, in the original film. And so one of the questions is, how is it that we're able to perceive what you just saw as an animated film as an actual bouncing ball or not? So there's a bunch of different ways that animation and animators go to work on getting motion into their work. So one way is simulation. And so these are some clips from some films that I have worked on in the past. You can see the tag here, kind of with its kind of beautiful dangling motion there. You could have seen the cord in the first piece. Here you see the balls and the spring on top of the head. Here there's a bunch of snow particles in the snow globe and this nice wiggling of the antenna on top. Now, in all four of those cases, people accused us of, using simulation. It's like, that's amazing. You guys simulated the physical dynamics in an incredibly accurate way. And it turns out that no, we didn't. The only thing that was physically simulated was the spring on top of the head of the tin toy, and even that we tweaked after the simulation in order to make it look more realistic. The simulation didn't look real. So we're going to come back to this in a little bit, but I want to talk in order about how we tweaked it. These rules come from Frank Thomas and Ollie Johnston of Disney, and these originated in the 40s. And they were rules for giving animation the illusion of life. And they weren't taxonomous, so you can see some of these things kind of, overlap a bit. But the important thing, and what we're going to talk about here today, is this notion of exaggeration, and more importantly, a specific type of exaggeration known as squash and stretch. Now, squash and stretch, so it's one of the first things you learn as an animator. And so we decided to start with a very simple concept of a bouncing ball and the behavior of a bouncing ball in animation versus in reality. So what you see on the top is a drawing of an actual ball bouncing over time and its position in space. And what you see below is that same set of drawings, but they've been exaggerated through squash and stretch. And the thing to make very clear to yourself is that the bouncing of the ball in the bottom panel is not only implausible, it's physically impossible in the current universe in which we live, where the atmosphere does not bend the ball or squash it on the way down and then stretch it out as it hits the bottom of the floor in such a way. Now, certainly some the balls deform, but they do not deform nearly as much as it is shown in that second panel. And we would argue that you can't even perceive it based on some data that we have, how much they actually do deform. So anyway, we came up with a computational model. It's got 6 parameters, a bunch of things that I won't get into here today due to time constraints. But what we essentially did is an experiment where we took balls of multiple bounciness, the COR or coefficient of restitution of the ball. The higher the bounciness of the ball, the higher the COR, the more bouncy the ball is. And the amount of exaggeration through squash and stretch placed on the ball. So here we see there are 3 different exaggerations denoted with an S here for squash and stretch. This is a tennis ball in terms of its bounciness or COR. On the left, you see an actual physical depiction of the tennis ball bouncing, and that's the diameter of the ball depicted there, sampled at, I believe, 60 frames a second for this particular slide, with no exaggeration applied. Then the next panel is with 2/10. Again, these are arbitrary units of exaggeration applied, and then 4/10 applied. And you can see that basically the ball gets squashier and squashier and stretchier as we increase the exaggeration. So what we did is we basically simulated 4 different bounciness. We used a bowling ball, a baseball, a tennis ball, and a ping pong ball, just to give you some ideas of bounciness that we had there. And we also used 10 different levels of exaggeration. And we presented people with stimuli like the one you just saw there, then the one you see over there, and we asked them to rate the plausibility of the ball. Is it behaving like a ball or not? And they basically ranked a series where they were just given, so here's 2 more, where they were just shown something like that. Here you can see a lot of exaggeration on the one on the left and a lot of exaggeration on the one on the right. These 2 balls were, just for your information, rated as not very plausible at all. So we would literally show them a single stimulus, the ball would bounce, and they would rate it 1 to 7. How plausible do you think that actually is for a ball, bouncing in the real world? So for the generic ball case, what you see here is these are the results. The x-axis is increasing bounciness, increasing COR. So as we go from left to right, the bowling ball is on the left and the ping pong ball is on the right. And then the y-axis is the amount of exaggeration. So the lowest point is no exaggeration. And that's basically, kind of think about that as our null hypothesis. Our null hypothesis would be that what people will prefer will be balls that depict reality as closely as possible. Now, the color coding is where the information is here. And the lighter the color coding, the more frequently preferred that particular combination of exaggeration and bounciness were. And you can see, so for extreme exaggeration up at the top, clearly not much preference. But as you can easily see here, it turns out that a large number of people actually said that that particular combinations with a pretty good amount of exaggeration were deemed plausible. And the 2 dotted lines are the 50th and 75th percentile in terms of plausibility. So basically, and there's a slight inverted U shape here, meaning that at the extremes of the scale, people did not want to see as much exaggeration. But in the kind of the meat of the scale there, people were very, very tolerant of a large amount of exaggeration. and still declaring the ball as being plausible or even preferable. So here's an example of the most preferred ball. Now and again, I want you to watch the ball as it squashes and stretches and notice that. Look how much it squashes and stretches. That was the most preferred, highest indexed bounciness and deformation for just a generic ball. So, and again, like we just said before, it's physically inaccurate, uh, but it's perceptually considered very nice depiction. So we did the experiment where we gave people in two other ways, where we gave people a little more information. Now we said, all right, how plausible is that for a bowling ball, right? For each one on the left. So we constrained the behavior based on the bounciness. And then we also did photorealistic renderings of a bowling ball bouncing like a bowling ball and a ping pong ball bouncing like a bowling ball, right? We were able to superimpose a bunch of different things, superimpose the depiction and the information you were getting, and it was either congruent or incongruent with the actual bouncing of the ball. Now, the data, and again, time constrains us here a little bit, but what I'd like for you to notice in all three of these cases, so left is just calling it a ball, and it shows that people were extremely tolerant of it bouncing. In the case here, for example, the baseball, which has the bounciness of this black dotted line here, it turns out that still half of the people involved saw a baseball that distorted a rather significant amount. They were still willing to call it a baseball. You'll notice though that they were biased towards less bouncy balls, which is consistent with what we know about how a baseball behaves. But the bounciness was not what they were more critical of the bounciness and less critical of the exaggeration of the shape of the ball. And the same thing when we depicted it photorealistically, you can see here that again the exaggeration goes down a little bit, but still people were willing to accept a large amount of variability in both the bounciness and in the shape of the ball uh, when it was depicted as an actual baseball. So the moral there, I believe, is that people are basically not so interested in the physical reality, but they prefer what looks good in this case. And Disney obviously knew all about that. So here's another experiment we did. These days, right? Disney, and this comes way before Disney. Max Fleischer and well before this. But Max Fleischer invented a device called the rotoscope, where you would use actual footage, and that footage would be traced onto paper. And then you can see here on the top the actual reference footage with the orange lines being what was traced, and then how it was actually transferred to an animated character. And you can see there's a lot of exaggeration laid onto the character, and that I would argue makes it look more convincing. And of course, we have tons of tools for doing this now in our own world, right? We have very high tech tools for doing motion capture. And so we said, all right, well, let's see. We can simulate, and maybe our simulation isn't good, but maybe we can measure motion in the world and see what happens in terms of people's preference here. We know from experience and reality that people have to tweak motion captured animation in order for it to look quote unquote good when it is used in motion pictures. So what we did is we did some face capture, and here is a actor expressing surprise, and their face being was motion captured into a system and then depicted using this kind of generic head here. We used five different emotions. We used surprise, fear, anger, and then here we also then depicted the character with exaggerated features. So we had a version of the character with exaggerated features, and then we had an animator exaggerate the motion as well. So the bottom line is we had 3 levels of feature size. So we had tiny features, normal size features, and large features, or exaggerated. Then we had an animator animate, kind of underplay the motion and then over exaggerate the motion as well. And what the subjects did is they saw a screen that looked like this, and they basically went through and selected which was the most convincing or plausible or preferred face in these particular or performance, and which ones weren't. And so remember, I said we have a 3 by 3 matrix. The horizontal matrix is the horizontal axis is the size of the features. So on the left are the small features, in the middle are the normal size features, and on the right are the emphasized features. And then the vertical axis is the exaggeration. And on the top are the under exaggerated, and on the bottom are the over exaggerated features, or so things played down and not played down. The darker the color, the more preferred the animation was. And what you see here are 2 different rankings. So you see, so we had I think about 100, almost 200 subjects rate these different animations. And what you see is for the highest ranked, in this case, anger, the most preferred had the motion exaggerated, but the features didn't really seem, the exaggeration of the features didn't really seem to play into it too much. It turns out that the motion needed to be exaggerated in order for people to prefer it. On the other end of the scale, you can see that these were the worst ranked or the most disliked, and the most disliked had motion that was not exaggerated at all. It's just normal, uh, uh, emphasized motion, unprocessed by the animator. And the ones that, so those were the most disliked. Basically, the ones that were most disliked had exaggeration of feature sizes, but without any commensurate exaggeration of the motion. And it turns out that this collapses across all the emotions. It wasn't just anger. They all ended up working this way. The most preferred had exaggerated motion, and the least preferred had no exaggeration at all. Things were not underplayed or overplayed. And the size of the features didn't really seem to affect it very much, other than the fact that people tended to really dislike big caricatured features when the motion was consistent with just normal, when the motion was unmodified or unexaggerated. So to conclude, it means that in both the simulated and in the captured scenarios we had, the physical fidelity isn't what's necessarily the most important thing. The phenomenological fidelity is what becomes important, and the phenomenological fidelity is emphasized by exaggeration, right? And exaggeration and emphasis of the particular motion, in the case of both the bouncing ball and the facial animation. Things that violated the rules in a positive way tended to be perceived as being more realistic and more preferred. And secondarily, the more specific the depiction, the greater the interaction is between the kind of realism, the parts of the thing that are real and the parts of the thing that are exaggerated. The more that interaction comes into play. Uh, so that's all we have for you today. I appreciate your time, and thanks for your attention.